We've all seen AI do incredible things, right? It can write poetry, ace exams, make unbelievable art. But there's this one huge, fascinating puzzle at the heart of it all. Why is it so darn hard to get AI out of the digital world and into our physical one? Well, today, we're going to figure that out. I mean, seriously, think about this for a second. We've built these incredible digital minds that can tackle things we consider the peak of human genius. And yet, a top-of-the-line robot can still be totally stumped by a doorknob. This isn't just some funny little quirk, you know? It's a massive clue about what intelligence actually is. And this whole mystery, it actually has a name, Moravec's paradox. It's this completely upside-down situation where the stuff that's hard for us humans, calculus, chess strategy, that's a walk in the park for AI. But the stuff that's ridiculously easy for us, like walking across a room or picking up a cup, is just brutally difficult for a machine. So what on earth is going on here? Okay, get a good look at this chart. I know, it looks a little complicated right now, but trust me, the answer to our whole puzzle, why an AI can write a masterpiece but can't open a door, is hiding in plain sight right here. And by the end of this, you're going to understand it perfectly. All right, so first things first. To crack this paradox, we have to get a handle on why the real world is just such a nightmare for an AI. It really all boils down to two massive hurdles. First, the digital world is clean. It's predictable, it follows rules. But the physical world? Oh man, it's messy, it's uncertain, it's dynamic. Doing the exact same thing twice never gives you the exact same result. And second, there's the data problem. You can feed an AI 1 billion pictures from the internet in an hour. But teaching a robot to stack a few blocks, that takes weeks of slow, expensive, real-world trial and error. And that is the absolute core of the problem. As the research paper puts it, physical interaction is just fundamentally uncertain. Think about it. A doorknob might be slick, a floor might be uneven, the door might be heavier than you thought. There's no single perfect way to open a door that you can just program in because the situation is always changing. And that uncertainty problem leads right into the next big issue, data scarcity. Every single attempt a robot makes, every failure, every success, that's one single piece of data. It has to be collected one at a time, in the real world. It's a huge, massive bottleneck compared to just scraping the entire internet. So, with challenges this big, how do you even start to build a machine that can actually act in the world? Well, it turns out there are 4 main schools of thought, 4 competing philosophies on how to get it done. So the first big idea, and this one goes way back to the 1940s, is called a world model. The basic idea is that the AI builds a little simulator, a mini version of reality inside its own code. It's like it's playing a video game of the real world in its head to predict what's going to happen next. It uses that to plan out its moves. If I push here, the door should swing open. It's basically intelligence through pure simulation. Now, the second philosophy completely flips that on its head. It's called embodied intelligence, and it argues that the brain isn't the whole story. The body itself, its shape, its sensors, the way it moves, isn't just a taxi for the brain. It's actually part of the thinking process. Intelligence isn't just software. It's the hardware and the software working together as one unified system. Third, you have this really cool idea called affordances. The thinking here is that you don't need a super complex model of the world in your head. Instead, you just learn to see the world in terms of what you can do. So a robot doesn't see a doorknob, it sees a graspable, twistable thing. A floor isn't just a surface, it's a walk-onable. It's a huge shift from just seeing objects to seeing possibilities for action. And that brings us to our fourth and final contender, physical AI. You can think of this as embodiment put into practice. This approach says, let's stop trying to solve everything with code. Let's actually build the intelligence into the robot's body itself, into the materials we use, the design of its joints, the shape of its hands. The smarts aren't just in the brain. They're baked right into the physical hardware. Okay, so we've got our 4 big ideas, our 4 main contenders. How do we figure out which one is actually best at solving our doorknob problem? Well, you do what anyone would do. You hold a competition, a virtual robot Olympics. So to settle the score, researchers built this incredible virtual lab. They created 4 different AI agents, and each one was built from the ground up based on one of those 4 philosophies. They had a world model agent, a purely reactive one, an affordance-based one, and a physical AI agent. Then they threw a whole bunch of tasks at them, everything from super physical to super abstract, and they just let them run. All right, remember this chart? This is the scoreboard. This is what happened in the robot Olympics. Just to reorient you, that line on the bottom, the x-axis, goes from purely physical tasks on the left to purely cognitive, brainy tasks on the right. And the line going up, the y-axis, is just their success rate. And right away, you can see the paradox in action. Look at that dashed purple line. That's the human baseline. We're awesome at physical stuff on the left, but our performance kind of drops off on the abstract stuff to the right. Now look at the blue line. That's the world model AI. It's a perfect mirror image. It's terrible at physical tasks, but a genius at the cognitive ones. But then, check out the red line. That's the physical AI agent. It is by far the best of the bunch at physical tasks, getting really close to that human level of skill. So what's the secret sauce here? Why is the red agent just crushing it in the physical world where the others fall flat? Well, the answer comes down to one single powerful word: embodiment. See, in the simulation, every agent was given what's called an embodiment coefficient, basically a score for how much its body contributes to its intelligence. And the results? They're crystal clear. The world model agent, which is almost all brain, has a super low score. But the physical AI agent, where the body and brain are designed together, it's got the highest score. It's a straight line. The more embodied the agent, the better it performs in the physical world. Period. But wait, it gets even more interesting. Let's zoom in a little. This plot here shows us the link between how well an agent perceives those affordances, remember, seeing the world in terms of actions, and how successful it is. And the pattern here is just wow. What the researchers found is absolutely fascinating. There's this magic number, a detection threshold at 0.6. Below that score, the agents are basically just guessing, flailing around. But the second their ability to see affordances crosses that 0.6 line, their success rate just skyrockets. It's like a light bulb switches on. And guess which agents are almost all on the right side of that line? Yup, the physical AI and the affordance-based ones. Seeing what you can do is a total game changer. Okay, so let's tie all this together. We've seen the paradox, the philosophies, the results of the robot Olympics. What does this all mean for the future of AI? The bottom line is this: if we ever want to build AIs that can actually do things in the real world, help around our homes, explore Mars, work in our factories, we have to stop focusing only on building smarter software. We have to start designing better bodies. Intelligence, it turns out, isn't just about thinking. It's about doing. And I think this quote from the paper we've been looking at just says it all perfectly. The next great leap for AI isn't going to be about describing the world better. It's going to be about acting in the world better. For decades, the whole story of AI has been about building better digital brains. But what this research tells us is that the next age of AI, the next great chapter, is going to be about building better physical bodies. And that leaves us with one heck of a question. Once we finally combined those brilliant brains with truly capable bodies, what will they be able to do? Thanks for joining me on this one.